Okay, thank you. And I would like to thank the organizers for inviting me. I've been enjoying the meeting so far. There are so many nice thoughts. And my name is Yasushi Fujiwara from Kobe University. And I have been working on surface waves and related stuffs, including language cyclations and so on. But today I'm going to talk about larger scale, like wave current interaction problem. This is a work I did in collaboration with Yoshimasa Matsumura and Hiroshi Tamura, and it was recently published. Okay. Yeah. So let me start from this picture. There are many processes going on in the ocean surface boundary area, out of which we are going to sort of feature the horizontal mass transport, because of course it's important for affecting floating materials, but also its horizontal convergence causes Ekman pumping, which eventually drives ocean circulation. And the classical theory for describing the horizontal mass transport is, as you know, is Ekman transport, which drives the volume to the right angle to the wind stress, but also the surface waves, which is almost always there, carries water towards its propagation direction, which is called the Stokes drift or Stokes transport if it's vertically integrated. And the Stokes drift is in general in the wind direction, but it's not always so because the remotely generated swell can influence the local wave field. And of course, it has a large impact on the horizontal transport of floating materials. And my general interest is that how do these wave-induced mass transport modify the ocean dynamics? So the original motivation for this study was on the coastal ocean dynamics. Because of the limitation in the fetch, the Stokes drift is generally from the shore toward the coast. And in order to conserve mass, the ocean current there needs to be some kind of like counter current to conserve mass. And how does it happen? So I'm going to start from a general introduction of the Stokes drift and Stokes transport. I think many of you are already familiar with the surface waves, like basic surface waves in fluid mechanics problem. This is linear rotational waves, which is also known as airy waves. And in order to have the trajectory of water particles, we need to sort of integrate the velocity field following the water particle trajectory. So in order to have the water particle trajectory, we need to have the water particle trajectory here. And to proceed ahead, we sort of assume that the water particle position is not displaced too away from its original reference position, which is fixed in space. And so we expand the velocity field. And if we take only the first order term, we have this kind of solution, which means that the water particles have like circular orbits, which is also called orbital velocity. And if we go up to the second order and also take phase average over one wave period, we get the Stokes drift. This is a first order term, which average comes to 0. And the second order term is the product between the displacement times the velocity gradient, and it does not go to 0. This is the Stokes drift. We can do the same thing for the vertical component of velocity, and we get 0 up to the second. And this is a calculation where there's no background Eulerian current, but even if there is a background current, if it's not too strong to break down the wave orbital motion, the relationship still holds, and we get this general relationship that the Lagrangian mean velocity is the sum of Eulerian mean velocity and the Stokes drift. And this is for monochromatic waves, but even for the wave spectrum, we can get the leading order estimation by simply superposing each contribution from each frequency component. For example, for Stokes transport, it is a first order moment in terms of angular frequency. Sorry, I think I should have removed this vertical dependence, but okay. So yeah, we can sort of estimate the total Stokes transport from the output of spectral wave models. And the general magnitude of the Stokes transport is actually not so small. So I did a rough sort of parameterized computation from ERA 5, and I have plotted like sort of the relative magnitude of the Stokes transport against the Ekman transport. And in the equatorial regions, the ratio is small because the Ekman transport goes to infinity. But otherwise, in mid-latitude or higher latitude, the Stokes transport is typically more than 30% of the Ekman transport, which means, well, I mean, we know that the Ekman transport has a large impact on the coastal dynamics, so we can also expect the impact of Stokes transport as well. Okay, so in order to incorporate the wave effect into the ocean models, people have used something called wave average equations. And ocean models nowadays they are high resolution, but still it's their horizontal grid scale is much larger than typical wavelengths of the surface waves. So we are looking at the prognostic variables of ocean models can be thought as a wave average velocity. So the subgrid scale phenomena's effect, including the Stokes drift, needs to be parameterized into such equation. But the waves are something totally different from turbulence, so we need to incorporate different theory, which is wave mean flow interaction theory. And so here I'm showing one typical set of equations that people use to incorporate the wave effects. This is called wave average equations or Greg-Leibovich type equation. So the blue terms are the wave effects. In the momentum equations, there is a gradient term called Bernoulli head. It sort of adjusts the pressure distribution. And this is the vortex force term, which is famous for driving Lamian circulations. And also here, this is a Coriolis force acting on the Stokes drift, which is called Coriolis-Stokes force. And for the mass conservation equation, the surface elevation changes not only due to the horizontal convergence of the Eulerian velocity, but also the horizontal convergence of the Stokes drift velocity. And for the tracer equation, we have the additional aggression by the Stokes drift. And finally, actually the Stokes drift velocity, by definition, it is not completely incompressible, but it has a small divergence in the higher order. But typically, people sort of neglect that compressibility and assume that Stokes drift velocity is incompressible and use this relationship to estimate the vertical, diagnose the vertical component of Stokes drift velocity from horizontal one. And this is done because, first, we don't need to sort of change the basic framework of the numerical ocean models, which is typically incompressible. And another reason is that even if we sort of approximate with the Stokes drift incompressibility, this set of equations holds basic like properties such as the mass conservation, tracer conservation, and potential vorticity conservation. So yes, so with this background, I'm going to I will try to give an overview of the like ocean current response to incoming Stokes drift field. And to do that, I will look at like two sort of limiting or extreme regimes in terms of timescale. The first one being the short timescale responses, and well, I will try to show like illustrative simulation results, and I will use the wave resolving numerical simulation results here, and then I move on to the longer timescale, in fact, superinertial timescale current responses, where the rotation starts to become important, and I will use wave average simulation in that case. And actually, in both regimes, there is a return flow response, and to distinguish them, I will call them a group-induced return flow for the short timescale one, and rotation-induced return flow for the long timescale. So let's start with the short timescale response. And to begin with, waves are not inhomogeneous, so they have like spatial group-like structure. Well, it's kind of obvious that wave pattern, wave height or Stokes transport generally follows the synoptic pattern of the meteorological like phenomena like cyclones and so on. So they are not uniform. There is like, for example, convergence or divergence of the Stokes transport. And even we look at smaller spatial scales, waves are loopy. Here I'm showing the observational results by Jerry Smith. This is a result from the horizontally looking sonar, looking at the radial velocity component, and we can see that there is a kind of like large amplitude pattern propagating away from the observation point. This is the wave groups. And there is a classical theory describing the ocean current response to this kind of wave groups, initially discussed by Longet-Higgins in 1960s, but the paper by McIntyre is also very famous. And yeah, when there's a sort of an isolated wave packet, it induces horizontal mass transport, and which leads to horizontal convergence and divergence of mass, which tries to sort of raise or lower the water surface. However, the long gravity wave adjustment tries to keep the surface flat. So the Eulerian velocity is kind of pumped in at the head of the wave groups and sucked up at the tail of the wave groups. And to retain the incompressibility, there is a potential kind of velocity response, which is over, which has a spatial scale of the wave groups. And in fact, if we integrate the volume transport vertically, there is no mass transport attached to the wave groups. And I will show that using wave resolving numerical simulations. So yeah, I will use a free surface numerical model that originally I developed to sort of explicitly simulate the Langmuir calculations. But this is a surface. This employs surface following coordinate, and so Langmuir calculation is a kind of a delicate phenomenon. So I pay special attention to the conservation properties of mass, momentum, and energy. And yeah, but in this case, we look at the vertically two-dimensional case, something like this, with sponge layer at both ends. The top boundary is a free surface, and the bottom boundary is flat. And yeah, the governing equation is incompressible. Incompressible Navier-Stokes equation. It is non-dimensionalized with respect to angular frequency and the wave number of reference waves. Things are very simple. There's no stratification, no rotation, but I impose a weak viscosity throughout the domain. And to produce waves in this ink region, I sort of oscillated the upper surface pressure boundary condition with a certain frequency, and then the waves are excited to propagate like to both directions. But the leftward propagating waves is immediately absorbed by the sponge. So the waves propagate through the domain, and it is eventually dumped in the surf zone. It's not actually breaking waves, but I sort of try to mimic the surf zone by imposing a higher viscosity out here. So this is how it looks like, the surface elevation. So the waves propagate towards the right with the group velocity of the carrier waves, and it is dumped when they enter into the source. So here is the current response beneath the waves. The top panel shows the surface elevation. The second panel shows the horizontal Stokes drift velocity components. The green color shows the rightward component, and the blue color shows the left. And the third panel shows the vertical distribution of the Eulerian velocity. It is kind of hard to see, but maybe you can see the pale blue color, which means that leftward velocity is sort of attached to the Stokes drift pattern, which propagates towards the right with the group velocity of the carrier waves. And also, this return flow is almost vertically uniform, so it's a barotropic. It has a barotropic structure. And in fact, if we integrate, here I'm showing the vertically integrated mass transport, the blue line shows the Stokes transport, and the orange line shows the Eulerian transport. So we can see that the Eulerian transport almost immediately locally cancels the Stokes transport. And this can be understood as the gravity wave adjustment, long gravity wave adjustment, because the propagation of the carrier waves or Stokes transport has a group velocity of non-dimensional group velocity of 0.5, but the phase speed of the long gravity wave, which is in the shallow water regime, is 3.54, which is much larger than the propagation speed of the Stokes drift pattern. So the gravity wave response occurs in a sort of a subcritical regime. So effectively, the rigid condition is almost always achieved. Yeah, so there's an immediate long wave adjustment to mass transport. And I also compared the response with the wave average simulation. So the equation that I have shown earlier. Here I'm showing, in the right panel, I'm showing the wave average simulation results. We can see that the surface elevation is almost zero. And I prescribed the propagation of the Stokes transport, limiting the results from the wave resolving simulations. And here I'm looking at the response in the Eulerian current. And we can see that the wave average simulation sort of reproduces the response both in like quantitative and qualitative sense.
Can you say something about the velocity Stokes?
Right. When the waves break or waves are dumped at the viscous region, they sort of lose momentum, or there is a like when the waves break, they inject a strong vorticity, lateral vorticity component. And yeah, that happens in the wave resolving simulation too. So here is a strong jet associated with a breaking waves towards the wave propagation direction, and there is also associated return flow beneath. Does it make sense?
It would be the wind stress or the stress?
In the wave resolving simulations, I didn't have any other tangential stress at the top.
The waves does the stress, right?
Right. And so that process is sort of explicitly simulated in this case. But in this wave average case, I sort of added additional tangential stress based on the virtual wave stress theory of longitudinals. So it's like the loss of pseudo momentum due to the viscous attenuation.
Yeah, so both are not perfectly equivalent, even
no.
mathematically.
The problem setting is the prescribed Stokes transport or the virtual wave stress here is not really like equivalent. I sort of mimicked. Yeah. Okay. So let's move on to the long time scale responses or rotation-induced return flow. And when we come back to the wave average equation, we have this term, Coriolis-Stokes force. This effect was actually originally addressed by Hasselmann and also derived in a like Leibovich style by Northern Fon. And this is from an Eulerian point of view, it arises as the convergence of the Reynolds stress associated with the wave orbital motion. In the rotating frame, the surface gravity waves become inertial gravity waves. So the orbital plane becomes slightly tilted towards the lateral direction, which means that there is a correlation between V and W here, and its amplitude decreases with depth. So there's a vertical convergence of the Reynolds stress. So that's how the Eulerian transport is derived. Eulerian velocity is forced. And the easiest case we can think is that the horizontally homogeneous and steady and implicit flow. So the force must be balanced by some force. And the only force that can occur is the Coriolis force acting on the Eulerian current. So when F is non-zero, we get this relationship saying that the Eulerian current locally cancels the Stokes drift velocity. This is the rotation-induced anti-Stokes flow, which results in net zero Lagrangian velocity. So yeah, this is what happens. So the Stokes transport, Coriolis-Stokes force acts towards the right of the Stokes velocity. And to balance that, the Coriolis force must act in this way, which means that the Eulerian velocity must have the same magnitude and the opposite direction to the Stokes velocity. Then this is the horizontally homogeneous or steady implicit flow. But how about the case with time-dependent or inhomogeneous forcing? So let's look into that using wave average simulations. So I use a non-hydrostatic, well, it doesn't have to be non-hydrostatic, but ocean model equipped with a wave average terms, and I force the current field with Stokes transport. So let's think of a rectangular domain. The x boundaries are the vertical walls, and I sort of assume that this side is a coast and this side is a shore. And in the y direction, it is periodic, and the upper boundary is a free surface. And I do the simulation in F plane, and there's no viscosity nor any stratification for simplicity. The waves come from the shore towards the coast. This is sort of prescribed Stokes drift velocity field. It has a vertical structure of a monochromatic wave with 10-second period. And I think about two patterns in along coast structure. The first being uniform, the second being like localized or confined structure in some way. And it also changes in time. So it starts from zero and it develops and it decays to zero over a time scale of 3 days. And considering the inertial period in this setup, this is a sub-inertial regime. So here, let's start with the Y uniform case. Because everything is uniform in Y, so I'm showing XT cross section. The first panel shows the Stokes velocity, and the second panel shows Eulerian velocity. The third panel shows the Lagrangian velocity. And the red color shows towards the right, and the blue color shows towards the left. So the waves come and decay. So you can see that, I think I will play that again. You can see that the Eulerian current almost simultaneously cancels the Stokes velocity. So we don't have we have almost no Lagrangian velocity. This is kind of expected from the anti-Stokes flow argument. So our whole forcing is in superinertial scale, so the inertial adjustment is almost always achieved. But then, how about the case with like localized forcing? Here I'm looking at the situation this is a bird's eye view looking down, and I'm showing the vertically integrated transport field. The left panel shows a Stokes transport, and it develops like this. The color shows the magnitude, and the arrows, which is a bit difficult to see, but arrow shows the direction. So let me show that again. So there is like localized Stokes drift coming towards left, and the right panel shows the Lagrangian velocity response. So it looks like this. So I think if you can't see the arrows, it's hard to see the actual response. But actually, there is a dipole like net horizontal circulations in the both sides of the localized forcing. And this is a vertically integrated one, but I looked at the vertical structure. Here I'm showing the vertical profile of its component velocity, and the blue color shows the Eulerian, the orange shows the Stokes drift, and the green color shows the Lagrangian. And it looks like the Eulerian velocity almost locally cancels out the Stokes drift velocity, but there is a small deviation from zero, which we can look at, we can see in the Lagrangian velocity profile. So Lagrangian velocity almost has almost like vertically uniform or barotropic residual pattern. And yes.
Would we also expect some kind of inertial oscillation?
Right. Actually, there is, but it's small because our forcing is like slowly developing. Actually, I have an animation with that like shorter timescale version, but maybe I can sort of show that later. Yeah. And the right panel is the force balance in y direction, and what we can see is the green color, which is the Coriolis force acting on Lagrangian velocity, balances with the red line, which is pressure gradient force. So it means that the circulation is geostrophic. In fact, the surface elevation field was consistent with the geostrophic pattern. So in order to understand that, we sort of analyze the linearized wave average equation. So because we are looking at large-scale phenomena, let us assume that the Rossby number is small and also hydrostatic balance. And let's linearize the equation with respect to the Eulerian and Stokes drift velocities. And so we drop the nonlinear terms and also the vortex force term. So we get this set of equation. Well, there is a buoyancy parameter. Okay, in our simulation, we didn't have any stratification, but I also included the buoyancy here. And in the left-hand side, the Eulerian, homogeneous system for the Eulerian velocity. And the right-hand side terms are the forcing induced by imposed by the Stokes drift. And we transform this into the Lagrangian velocity form. So this like by moving the term from the right-hand side towards the left-hand side. And we end up having equation which is a bit similar in the forcing in sense. The only forcing term is in the momentum equation, like this, the temporal variation of the Stokes drift. And we further decompose the Lagrangian velocity into local and non-local responses following the procedure done in the textbook of Eul, and into like local and non-local responses. The local response is the like velocity response at the local forcing. So there's no like pressure gradient for a term that sort of propagates the information in spatial sense. And also the local response velocity retains the incompressibility. So we can sort of calculate the local response velocity by pointwise time temporal integration of the Stokes drift velocity. It is noteworthy that the long-term average of the local response velocity is 0 because in this term the temporal variation term disappears. And this corresponds to the location-induced pointwise local anti-Stokes flow. And all other leftovers are the non-local responses. We can obtain this equation by subtracting the local response equation from the original one. And so the left-hand side is the homogeneous system for the non-local response, and the right-hand side represents the forcing. There are two forcing terms, one in the buoyancy equation, the other in mass conservation equation, but this like the first term is actually not so big, small, so not so big. So and the main forcing term is this one. This is the vertical component of local velocity at the water surface. And it is induced by the horizontal convergence of the local response. And this can be understood as the effective Ekman pumping. So oops. Oh yes. So we denote this with WX. And actually, one of the reviewers of the paper suggested me to call it Stokes Ekman pumping. So I will do that. So from this viewpoint, how can we understand the simulation results? So when the waves start from 0 and it develops, during that process, the local response equation is balanced like this. Because the forcing is in like superinertial timescale, this like temporal, the Coriolis force dominates the balance. So it ends up in this direction. So we get the local response velocity in lateral direction to the increasing Stokes drift, which causes horizontal convergence and divergence of mass, which leads to the Stokes Ekman pumping at both sides of the localized forcing. And this adds like the potential vorticity anomaly, which leads to anticyclonic and cyclonic geostrophic current at both sides. And this is about when the waves start from 0 to like certain value. But when the waves decay, the opposite thing happens. So the circulation disappears. And what's interesting here is that the response has a scale dependency. Well, I don't go too much into the detail, but from a brief scaling analysis, we can have this kind of relationship. So the resulting Lagrangian response is scaled by the incoming Stokes drift velocity time divided by certain value related to the spatial scale of the forcing L. When the spatial scale of the forcing is much smaller than the deformation radius, the denominator is almost 1, so we get Stokes almost the same order as the Stokes drift velocity, which was the case in our earlier example. Okay. Yeah. I don't see why we are not seeing the pointer. Maybe I can use this one. Okay. It's small, but yeah. And okay. Right. Thank you. And in the case where the faulting is has a spatial scale much larger than the deformation radius, it approaches zero. In fact, I extended the whole situation in horizontal direction by 100 times, which results in a very large scale forcing and responses. We get a very small response in here. So the net circulation selectively occurs for small scale wave inhomogeneity. And yeah, and it gets more complex if we have a stratification, because we have not only the barotropic deformation scale, but also a baroclinic deformation scale, which is typically much smaller than the barotropic one. And for example, when the forcing is larger than both barotropic and baroclinic spatial deformation radius, both barotropic and baroclinic responses are zero. So we end up having a very small response in both upper and lower layers. But the forcing spatial scale is between the barotropic and baroclinic deformation radius. Only barotropic response occurs, so we have a response in both upper and lower layers. And finally, the spatial scale is smaller than both barotropic and baroclinic deformation radius. Both barotropic and baroclinic response occurs, so the net circulation occurs is confined in the upper area. So finally, I did a simulation with a realistic setting. Like realistic topography, it's like Pacific side of Japan. And I also forced the situation with hindcast using wave-induced Stokes transport. But the ocean configuration is still very simple. There's no stratification, no viscosity. The forcing is Stokes drift related terms only. So yeah, I'm showing the development of the wave height and the Stokes transport. So here is how the response looks like. The left panel is the Stokes transport and right panel is the Lagrangian velocity. So accompanying the passing of cyclones, there is some events with high waves and strong Stokes transport of order like 1 meter square per second. And so yeah, for example, like this. But even after the cyclones has passed by, there is a strong like undulating transport pattern remaining in the Lagrangian transport field. And the fluctuation propagates southward. And this is actually topographic Rossby waves, because the Stokes Ekman pumping sort of induces the potential vorticity anomaly, and it sort of propagates following the the contours of background potential vorticity. And finally, I did a rough estimation of the influence of the waves compared to the wind. So this is a vertically integrated momentum equation. There are two terms, the first being the wind stress, the second being the Stokes forcing in Lagrangian form. And I calculated the histogram over this region, and it looks like this. The blue line shows the histogram of the relative magnitude. So as we can expect, the wind is the most dominant force in a mechanical sense. But the Stokes drift is, its median value is like maybe 3% or so. But in some cases, it can reach up to like 10% or 20%, which may be influential in certain problems, such as the short-term ocean predictions of coastal regions and so on. So here's the conclusion. We studied the current response to the Stokes transport. And first, the gravity wave adjustment cancels the transport. But if the forcing is sustained for a long time, the rotation effect comes into play, and it sort of locally cancels the Stokes transport. But that's not the everything. If the Stokes transport field is not homogeneous, it induces effective Ekman pumping to produce geostrophic current and topographic Rossby waves. And here are some random ideas about future directions. The first is that I think, well, we neglected the nonlinear terms. Well, the simulations were done with a full set of equations, but we looked at like large spatial scale phenomena. If the nonlinear terms are also important, maybe with like some mesoscale, spatial scale or so, then such nonlinear effect can sort of induce like irreversible change to the circulation field. And also, from the argument, the scaling argument implied that the smaller spatial structure induces net circulations, and the wave field is mostly associated with the wind. And I sort of incorporated the Stokes forcing in one direction. But the ocean currents also modify the Stokes transport field, and it can cause a much smaller spatial structure. So what if we couple in both directions the wave simulations and the ocean simulations? And there may be some like feedback effects or positive or negative or whatever, and which will have an implication for effective modeling of the ocean wave systems. Okay, that's it. Thank you very much.